BSides DC would like to thank all of our sponsors, and a special thank you to all of our speakers, volunteers, and organizers for making 2018 a success.
Dobre utro. Good morning. How are you? My name is Dave Riley, and I showed up early so I could set up in case there were any mishaps, and there were. So here we are. Like I said, my name is Dave Riley. I'm presenting on reverse engineering vintage systems, although I only cover a sliver of everything that there is to be covered. So there's certainly further reading to be had and lots to talk about. You're welcome to contact me at any of those two locations if you want to talk more. So about me, I'm a former-ish embedded engineer. In past lives, I've done hardware, software, and FPGA work. I still do occasionally, but right now I'm an API programmer. I'm also a computer necromancer. I work with a lot of formerly dead computers and ones that really just want to take a very long nap. My preferred architectures generally to work with, I like vintage Macs a lot. I grew up with them, so I'm very fond of them. And they also have a very interesting architecture. I also work with a lot of PDP-11s and other DEC stuff. 8-bit micros, 6502 and 6809 are my favorites. So this presentation is going to be biased a little bit toward those categories, but there's many others when it comes to vintage machines. Definitely not qualified to instruct on this stuff. Who really is? It's half archaeology, half embedded systems, and then the third half is magic. I'm currently employed at FireEye, but I submitted this talk before I was hired there, and I'm an API developer there, so if you don't like this presentation, do not blame my employer. That's all on me. But I hope you enjoy it anyway. So what kind of vintage computer are we talking about? How vintage specifically? There's religious wars on this subject. What qualifies as vintage? When I really got into the hobby about 10 years ago, the general gist was anything about 15 years old or so. And these days, it's a little bit harder to say. There's, 10 years later, there's more computers that you could consider vintage. And what really qualifies is, again, up in the air. Most people don't really think old PCs when they think vintage, although they can qualify, and more that's becoming a thing. People reviving DOS games and that sort of thing. Certainly relevant for this topic, for security. But I'll mostly be talking about systems from the late 70s up through the early to mid 90s. And so that covers things like late PDP-7s, because the earlier ones usually aren't in operation anymore. Early 8-bit PCs, like Apple II, Commodore 64, Trash 80. All the way up through sort of the peak zenith of the VAX, Alpha, Spark, MIPS, Netware time period. Also pre-iMac, Macs, PowerPCs before the New World, that sort of thing. One easy metric for whether you could consider a computer vintage is it old enough to vote? That probably fits. Unfortunately, now that includes computers made in 2000, and I don't really want to accept that, but here we are. And yes, these machines are absolutely still around. They're even around in places where you would really care about them failing. And if any of you are ICS people, probably about 80% of this presentation is going to be pretty familiar to you because almost all ICS stuff involves a lot of vintage machinery. Agenda for this talk, why vintage systems? I'm going to talk about why we care about them, why we should care about them even if we don't, and why you might want to. Where to start in terms of finding out about them, getting into them, that sort of thing. How do we break them? So for the red team, how do you get into them? How do you penetrate them? How do you convince people that these things need to be fixed or replaced? How do I protect them? So for the blue team, what do I do for a machine that hasn't had an OS patch since 1998, but is still controlling some important giant piece of machinery? And then for the yellow team, for lack of a better term, when do I replace them? That can be a deep topic. It's not just, hey, this thing is old, it needs to be replaced, because oftentimes, if it were that easy, it would already be done. So, why do we care? computers are usually still in service after 20 to 40 years for three main reasons. Number one, they're very important. Maybe they're controlling something big and dangerous, like trains or nuclear power plants. Number two, often they're very forgotten. Someone has put a server in a closet somewhere and it's lived there since 1984, and it's still, delivering the mail or news groups or whatever, and so as long as it's still running, no one bothers with it. Number three, someone important is lazy or cheap, or both. Because it's easier to not replace a computer than to replace it until it breaks down. And these really are the ultimate unpatched systems, and in a lot of cases, unpatchable, unless you're going to do the patch yourself, which sometimes you have to do in something that's critical. So, just how important are we talking? Critical process control is a pretty typical area you'll see older things. Again, like I said, ICS, big area for vintage machinery. There's a lot of multi-bus systems and VME systems still running machinery and trains and everything else out there. In fact, I think the London Underground still runs on multi-bus, or at least a big part of it does. And there's lots more in industrial, like steel mills. Our nuclear launch system still uses an old IBM system with 8-inch floppies, which, is sort of good news because 8-inch floppy drives are easy to repair, but the media is not, so, not great. The benefits of the replacement may not be worth the cost and the risk. Sometimes just in someone's opinion, sometimes it doesn't wash out. So, if you're talking about something like a giant steel mill, if you replace it, it's going to cost a lot to do it right. It's going to cost, man years, it's going to be mountains of documentation, but you also want to weigh that against what happens if the old machinery breaks down and we can't replace it because these things haven't been made since the 80s. And don't generally underestimate the value to a business of something that's known working. There's the old, if it ain't broke, don't fix it. Again, with critical things, that's important because the cost of failure is extremely high. Also, the original developers and maintainers are almost certainly long gone on a lot of these things, so the ramifications of the replacement or upgrade may not be particularly unclear, or may not be particularly clear because the people who wrote it and maintained it before aren't around to give advice. So it's a good reason why those are often not replaced. As far as being forgotten about, everyone either has or has seen server rooms that look like this. This looks actually a lot like my basement, even though it's not my basement. Things get forgotten and buried, especially in, let's say, small to medium-sized businesses that have survived long enough, and these servers get set up, they get put up, under someone's desk, that person leaves, it becomes sort of the de facto server corner, and, there's credible stories of NetWare and VMS servers being found behind drywall because someone put a server into a closet, later the workers just patched up over that closet, the machine was still running, and nobody knew about it until the mail stopped coming one day, and they're like, well, what server handles that? And they had to trace cables back through drop ceilings, and eventually they found it behind a wall. These things happen. And of course, those operating systems have fantastically long uptimes, so. And of course, if no one but facilities management goes into the wiring closet at your work, how would you, the third generation employee at this office necessarily know about the old VAX that's been running the accounting system that everyone has pretty much forgotten about? So finding those can be a bit of sleuthing work. And then, of course, the third reason, laziness or incompetence. Sometimes things don't get replaced for really dumb reasons, especially in government, because once you add bureaucracy to things, it just takes a lot of time and effort to replace things, because everyone's afraid of getting fired. No one wants to lose a government job because they don't always pay well, but they're at least pretty static. For example, the Department of Defense will still pay big dollars for a particular microvax model or VAX station because it's on the checklist for a mission-critical app. And so on eBay, all the other members of that family are going for $100, and this one goes for $3,000 because the DoD will still pay that for it. And no one wants to get fired for purchasing the wrong thing or moving it to some emulation solution, which will probably work but might not. And then, of course, sometimes management just won't replace a system that's still working, usually because technical debt is a really poorly understood effect in a lot of circles. the understanding that it takes twice as much effort to replace something farther down the line is a little bit alien to folks, and it's difficult to explain. But that's why these things stick around, and the places you'll find them. So, where do we start? Well, if you want to start finding them, again, safety critical systems, power plants, heavy industry, lots of ICS stuff, trains, anything nuclear. Basically, anywhere you see computers controlling really big, expensive machinery, it's likely. Also, long-lived and expensive systems that have custom interfaces. So, a lot of hospitals, are famously still running like Windows 3.1 for running their MRI machines. A lot of electron microscopes have interfaces that were only available for old Macs or PDP-11s or whatever, and they still work. And unless you're going to build your own interface, you're not going to be able to use your electron microscope. So. Unless you're in the mood to buy a new one, you keep things running. Lots of other big lab systems. Lab equipment is notorious for just kind of having hacked together interfaces to computers that may not be replaced very often. Less often, you'll see them in everyday use. So old servers that never migrated, like your old mail or newsgroup server that's still been chugging along until one day it doesn't. Everyone's gone to an auto parts store and you see them still plunking around on a VT220 to check out your brake pads or whatever. They're still running an ancient POS system that works absolutely well enough for them, so there's not much reason for them to change, at least as far as management's concerned. Old computer labs also. Universities frequently just don't clear out the room until they actually need the room. So my alma mater actually advertised that it was still running Onyx's, SGI Onyx's up until about 2 or 3 years ago when they revised the course catalog. Although I'm not sure they still were. So. Often these things are physically obscured. So like an old computer lab no one uses, or a wiring closet, or something that gets patched over, they get forgotten because the people who maintained them leave and no one's cataloging them anymore. So it's chalk another one up for asset inventories. Very important. Before you get into things, always be cognizant of legal things. So there's the standard potential legal disclaimers. Even vintage software may still have licenses that are still in effect forbidding reverse engineering. That may or may not matter, depending on what you're trying to do with it. It has the same legal hazards as reverse engineering modern software and hardware, because people do get sued for that, but it may be hard to find out who actually owns the IP now. Some of these companies have been bought and sold 3 times, and you'll find that the company that actually owns it now says, well, we don't have any record of that, but we will still sue you if you try to take it apart. So some companies, especially defunct ones, because they can't, won't sue you if you're not harming their commercial interests, but of course, some do anyway because they're jerks. And some also have a funny idea of what might harm their commercial interests. Sometimes they're also right, but a lot of times it's the lawyers told us to do it. There's also physical risks, of course. And again, if we're talking about things controlling large industrial systems, be careful when poking at things that you might break, because you don't want to be destroying a $10 million piece of machinery because you brought something down with a port scan. Older hardware often didn't have as many safeguards on it, so you could configure things in ways that could actually damage the hardware. That's true of new hardware too, but it's less common. And of course, it's just old. I mean, old hard drive platters are just spinning rust. They've been spinning for 40 years maybe. Sometimes they just stop working. And if you're really exercising them, they may stop working quicker. So, with that said, how do we break them? How do we get into them? This is actually the most reverse engineering part of this talk, but we'll get to it. So, what are we trying to do with these old systems? Why would you need to know this as a red team member, let's say? Standard red team stuff. You want to get into a system, you want to gain access, you want to dump critical data, you want to see if you could potentially break it and cause a lot of financial damage. And so you'll want to try networks. A lot of these things are networked. Some of them aren't. Many of them aren't. Some of them were pre-standard networking, so there's lots of different interesting network protocols that don't really exist anymore. They may be physically isolated, and that can still be important. Again, if we're talking about things like ICS, having physical access is sometimes just something you have to assume an attacker has had, and you want to be able to make sure that they're at least not easily able to get in and break things. You might want to manipulate data. If it's an accounting system, you might want to be able to pay someone extra, something like that. Or DOS important things. Anything that you would want to do with a modern system, it's pretty likely that you would want to do with a vintage system, except maybe distribute malware over the web. That's probably not going to happen. Short of that, nothing changes under the sun. How do we get in? So we talked about networks, physical access. RCEs abound. There's lots of them because, while a lot of these things went under code review, a lot of them didn't, and the hacking community was not as distributed back in the day. There are a lot of things that were never found. Privilege escalation on multi-user systems can be a big one. So for example, in VMS, now called OpenVMS, just in 2017, there was a privilege escalation to system found that went all the way back to VAX VMS 4, which was released in 1984. So that's a 33-year latent bug in a safety and security critical system that the Department of Defense and Guinness and other people use still. So there are still lots of things to be found and lots of things that were never found. That you can drop a 0-day on a 33-year-old system if you want. There are hardware firmware bugs. So we're coming back again full circle to this now, where we're finding out things like, our network cards are actually just tiny computers that can also be hijacked. Well, this was also true in the 80s. For a different reason, same and different reason. The host computers weren't as powerful, the buses weren't very fast. So for example, a PDP-11 Ethernet card is a 68,000 computer that does the job of sending and receiving the data over Ethernet, and then when it's got a bunch of stuff, it DMAs it into the host's memory. You can exploit that if you find a bug in that 68,000 computers program and overwrite it. So, and nothing really changes, but these things are out there, and the nice thing is those are a little bit easier to disassemble than some custom weird microcontroller from Intel. Also, lack of good access control. Certainly, especially if we go back to the 80s, especially if we go back to early micros, there may not have been any access control. So if you have physical access, game's over, you can pretty much control it. Other ones, especially early ones, were very limited, like very limited password length. RSX11M on the PDP-11, I think it's an 8-character password max, and I'm not even sure it's case sensitive because the entire OS isn't case sensitive. Lots of old backdoors left around, lots of default configs. Certainly a lot of earlier versions of VMS had default passwords for field service, which was basically a system config. So, and there's hardware debug options. So a lot of them made it really easy to get in and debug the hardware because if you were assembling a computer like this, you probably needed to do some of that. So those things are still left open. It's just like leaving an open and unprotected JTAG port on a modern router, something like that. A lot of ways to get into the older systems. Also, there's not much encryption. The older hardware just didn't really have the horsepower to encrypt much and do anything else at the same time. You can do AES on an Apple II if you want. You just need to come back to it next Tuesday. Most networking also assumed fairly benign host networks. Obviously not all of it, but if it was built at a time, let's say it was in a university AI lab, and it was only ever going to be AI students accessing it, they may not have really ever expected much to happen to it, but things change. Again, ICS has this same problem, that's why they keep those networks separate. TLS also was not a standard till the 90s when it was invented by Netscape. So everything earlier is custom, and a lot of places just either didn't do it, or if they did do their own custom crypto, it had the usual effects you would expect from custom hand-rolled crypto from people who didn't know what they were doing. So encryption is usually not something you have to worry about overly much. There's also, of course, weird networking protocols and hardware that you may not have heard of before, that you may have hard times getting equipment for. Unusual hardware like ArcNet. Token ring isn't that unusual because I think IBM still uses it, but it can be harder to get on a newer machine. Local talk for older Macs, DEC DDCMP, which is just serial. SDLC, X25, that's just a tiny sliver of the things that might be out there. You may find yourself needing to cobble things together. Fortunately, that's actually easier now than it used to be because it's easy to get things like FPGA evaluation boards that you can do with that, or BeagleBones, that sort of thing. There's also lots of protocols, and Linux actually still supports a lot of the older ones, which is nice, and TCP/dump understands even more of them. So AppleTalk, DECnet, and related, IPX, those are still supported by Linux. They're still supported by some of the BSDs, and you can still listen to them with TCP/dump or Wireshark, that sort of thing. There are quite a lot, especially if you get into the IBM world, that are a little unusual, but IBM actually keeps them maintained. So you will, if you're trying to go into a vintage network, you may have to do some deep digging on a lot of these protocols to figure out how to actually talk them. So with that all said, what's already available for vintage research and reversing? So the nice thing is the vintage computers and systems are often really well documented compared to the modern systems. So if you go and look up manuals on PDP-11 processors, they will tell you exactly how every block of it works. And part of that was because every block of it was on a separate card about this big that you put into a rack for the early ones. So if you had a broken one, you needed to know how to fix it. But it documents everything down to a bit level. And there are a number of archiving organizations that are dedicated to preserving all of this history. So BitSavers is a big one. Archive.org also serves up BitSavers information, but does its own archiving as well. So a lot of the service and operation manuals for these older machines are still around and available if you look for them, unless they were incredibly proprietary. And even then, sometimes they are, because people just had them lying around in a binder that they took home from work one day. Sometimes even schematics and diagnostic guides, especially if you get into service manuals. And if you're lucky, things like theory of operation guides and assembly listings. So how this really works with comments, which if you're trying to find a hole in something can be a holy grail because, oh, you didn't check the bounds on that. Great. Unfortunately, of course, it was a long time ago, and it was a time that not everyone was really concerned about preserving history. So a lot of documents were lost to accidents or careless storage. HP just lost a huge trove of documents that were waiting to be scanned because of a warehouse fire, I think. Also lawyers, again. A lot of lawyers don't want things getting out if they don't have a reason to be out, and will just forbid it, and then the documentation disappears, which is a shame. But usually, there's something available. So if you're trying to get in, do your homework up front. Do a thorough search to see if the thing you're trying to find is documented somewhere. I talked about archive.org and BitSavers. A lot of that stuff is OCR'd. So if you do searches for things that you're looking for, it'll pop up on Google a lot of the time because it's OCR'd actually well enough for Google to understand it, which is good, and you can find it. There's no need to rediscover the wheel if it's already documented, unless you really want to. If you really want to find out how these things work, the best way is to dive right in. If you're just trying to do your job, it's not going to be the fastest way, and it might not be the most effective way. Someone else also might have solved your problem. So you don't need to write a custom AppleTalk listener because TCP/dump still understands it. Someone might already have written a program to route DECnet over the internet. In fact, they have. It's called HECnet, and you can use that to your advantage if you need to break into things remotely. There's lots of old tricks still out there. Usenet archives are full of them because that was what people communicated on before the mailing lists, and that lasts forever. There's also now modern vintage computer group forums and mailing lists, which if you're interested in this, I highly suggest you join because you can ask questions of the people who actually used it at the time or the people who have been researching it in the meantime and have learned all the fun tricks. Worst case, buy an old sysadmin who knows a thing or two about what you're looking for a beer and ask about their tricks, and they will probably still remember it unless you've had too many beers. So, for example, talk about do your homework up front. Part of what you want to do is get familiar with what you're looking at. So this is a scan of, not actually mine, but the same model of my PDP-11 SCSI card. It's a SCSI card, but it's also an 8086 computer that runs a specially formatted DOS executable. I found all this out because my SCSI card broke because of a dumb thing I did, and I needed to fix it. And it turned out to be a bug in the firmware. But taking just a look at the card, if you're familiar with the older computers, you can already see a couple of things. Like you have what's clearly under these stickers, a CPU and a pair of EEPROMs, which means it's a 16-bit computer. And if you look at a couple of the surrounding chips, which you certainly cannot see from the back, you can see things that only ever existed on Intel 8086, unless someone was crazy. So that was enough of an intro to say, well, I can just pull those EEPROMs and dump them, and I can probably disassemble them with any standard DOS disassembler and figure out what's going on. And I could, and it did, and it worked. But you might not be able to spot it that quick if you hadn't already been looking at a lot of older computers. So getting to know the context in which you're going to be operating can be incredibly valuable, if for no other reason than you can just say, hey, I've seen that. So, other things that might help. Lots of old systems were reconfigured by building from source. So, actually still BSD Unix, like NetBSD, OpenBSD, FreeBSD, you can still install and uninstall drivers by rebuilding from source. Linux is similar. The whole system comes with commented C code. Even commercial systems like VMS and RSX11M, they reconfigured by rebuilding themselves, and they basically came with stripped and obfuscated assembly code or other code for rebuilding when you changed your configuration. That's a little bit easier to reverse engineer from than trying to take a memory dump and move outward from there. Of course, anything based on Unix really set the bar high on that because the whole operating system came with its source code. Obviously, the proprietary Unixes were slightly different, but still. Compilers and CPUs also were comparatively simple back then. So there's not a lot of optimization in anything that's compiled, so you're not going to have to be, trying to wrap your head around stupid compiler tricks like, declaring two variables in a single register, that sort of thing. Because the CPUs didn't have multiple execution units for the most part, the pipelines were non-existent. All an optimizer did was get rid of, garbage collected references, things like that. And so the code is usually very easy to follow unless it's intentionally obfuscated, especially handwritten assembly because it was written by a human who needed to read it again. And often the OS facilities were written with assembly programming ease of use in mind because they assumed everyone would be writing the programs in assembly. So the way you interacted with it was based on that rather than a bunch of C function calls. So it can make it a lot easier to read what's actually going on there. More things that might help. The hardware is generally a lot easier to physically probe if you need to than modern hardware. If you need to dump a ROM, you don't have to desolder a BGA package. You can just pop it out of a socket a lot of the time. Or if it's soldered on, it's easier to desolder, number one, but there's also clips that might work that could override the signals while it's powered on and read it out. DIP packages are really easy to clip scope and logic analyzer probes onto, much more than surface map packages. There's also custom clips that exist for popular families like 68030 in QFP package. You can get a clip that just sits right on that chip and you can plug it right into a logic analyzer and see what's going on the bus. And then also the buses are usually narrow and slow enough to attach logic analyzers to. So if you get an HP 16700 family logic analyzer, which you can get on eBay, although the shipping is going to be a lot because they're heavy, they're amazing, and you can bypass the license manager on it to get the licenses for the inverse assemblers, which will basically disassemble what's going across those buses live. So if you're out of options and you just really need to see what the processor is doing right now, it's a great option. The code sizes are also often very small. So for example, the PDP-11s, they only have 16-bit virtual address space, and same with 8-bit micros. So Unix on PDP-11, for the earlier machines, which didn't have split instruction and data space, those Unix programs could only be 64K in instruction and data. Doesn't leave a lot of room, but it also means if you're trying to disassemble it, you're not going to have to go too far. For more advanced operating systems for systems of that era, like RSX11M, there were complex overlay mechanisms that can make it harder to read, but it's comparatively rare. Things to watch out for. So even ancient code from the 80s still employed anti-reverse engineering techniques because reverse engineering was still going on. Certainly there was a lot of espionage back then. I know Digital put some fun things in the die for some of their chips so that they could see if they were being copied by the Soviets, and they were. I think one of the VAX dies had when you care enough to steal the absolute best, and it popped up in the Soviet clones. And sometimes there's clever techniques that make reverse engineering harder too. So unconventional branching methods like branching to the indirect target of some register can make it hard for a disassembler to follow the flow, especially if it's an older disassembler meant for that particular target. Branching into the middle of existing instructions. Sometimes that's for obfuscation. Sometimes it's just because you needed to cram something into a very tiny space, and that was your only option. One of the boot ROMs for PDP-11s does that because it only had, I think, 128 words of space for a very long boot process, and it actually branches into the middle of an instruction because it was able to reuse that particular value as another instruction. That's very hard to disassemble. Self-modifying code was actually fairly popular back then because, number one, it didn't break any kind of emulation or JIT compiler, so no one really cared. But number two, you could do some things to save a few cycles or some space or confuse your competitors when they were trying to disassemble it. And so unless you have some really fancy plugin for IDA or something, those are hard to do, disassemble automatically. Packing into data sections, same thing malware and other packers do now. Done a lot for compression too. Virtual machines and bytecode interpretation, that's also used for compression. The Apple II at one point had a 16-bit virtual machine interpreter in there that was incredibly slow, but also was incredibly compact code, and so you could use that. But you'll see that in older code a lot. I think actually all the original Microsoft Office programs for the Macintosh ran on a virtual machine as well. And of course, you'll see encrypted and encoded and compressed strings, just like you do now. So as far as how you get in, there are standard system tools. So a lot of vintage machines have built-in debug modes or monitors. You hit a key combination or send a serial break condition or something like that, and you'll pop into the monitor. So on Spark machines, there's OpenProm, which is the same as open firmware on the Macintosh. On newer PDP-11s, there's ODT, which is basically just a serial version of the front panel console switches. You can just go directly into memory and do whatever you want there. VAX Alpha System Console was basically the next iteration on that. You can get full access to everything if you have physical access to the machine. And in some cases, like I said, just a serial break sequence will dump you into those things sometimes. Especially if that was never turned off by the person who was setting up the system. And since lots of vintage systems were written in assembler, there are extensive machine code level debugging solutions in a lot of the operating systems meant to run on these things because that was the only way to debug them. There weren't a lot of source level disassemblers back then, and often they were very expensive and didn't come with the system. For offline work, of course, there are lots of reversing tools. Some of them you probably know pretty well, some of them you probably don't. There are a lot of interactive disassemblers. There are more these days than ever because people keep writing new ones, which is nice because it means IDA keeps getting cheaper. But they all have benefits and drawbacks over each other, especially when it comes to weird CPUs and vintage ones. So IDA, of course, is the big one. It has a very long history in reverse engineering, and as a result, it also has a huge selection of CPUs and binary formats. So it includes things like PDP-11 Alpha, 6502, especially if you have the Pro version. Lots more. Doesn't have VAX for some reason, but chances are 80–90% of the time you'll be able to find whatever target you're trying to disassemble in IDA. The only problem is, of course, it's expensive. If you're working for a company and you're part of the red team, that may not be a big deal. But if you're an independent consultant or a hobbyist, it's maybe not so great. And they have a free tier, but it's x86 only. So, Radar 2, which I never know how to pronounce properly. Newer open source disassembler. It is free. It's not bad. It's not spectacular a lot of times, especially for non-x86 architectures. It's not bad for ARM. I found it pretty much unworkable in its current state for PowerPC, but your mileage may vary. It doesn't have as many CPUs supported as IDA, but part of that's just it's newer, and people are writing new ones all the time. You can always write your own, just like you can for IDA and everything else. So if you have the time to devote to it, you can always write a module, and that may make your job easier. And of course, again, it's free, and it is improving rapidly. It is getting better at a very nice pace. If you're looking specifically for classic Mac stuff, this is the definitive solution. It runs on the classic Mac, Steve Jasek's MacNosy, which is the disassembler, and the debugger, which is the system-level debugger. It gives you the capabilities to go a lot deeper than Apple's development tools go, and it is an interactive debugger, very much in the vein of IDA. It works very well. It has a very funky interface because he pretty much just wrote it however he wanted, not keeping to the interface guidelines from Apple, but it is the way to go if you're trying to get classic Mac stuff, or really even any 68K stuff done, because it does such a good job with it. And it does things with classic Mac idiosyncrasies like resource forks that IDA really can't handle, and radar and everything else. Doesn't work under the classic environment in OS X. The debugger doesn't anyway, MacNosy does. But it will work under emulators like Sheepshaver, other PowerPC emulators. So if you find yourself needing to disassemble any of these for whatever reason, they're excellent tools. And if you need a real machine, find a vintage computer group. You will get more than you want. Binary Ninja, it's a new kid on the block. Pretty good, actually. It's commercial. It does a neat thing where it basically lifts things to a higher level intermediate language so you can examine the higher level program flow better, which is nice, and it's also fairly extensible. It's cheaper than IDA Pro, and actually it's more expensive than this now, I think. Oh, maybe it's not. Maybe that's actually still correct, but that is still cheaper than IDA for either version. It's very scriptable. It's a lot more friendly to modern UIs, if that's your thing. It doesn't have nearly as many processors and binary formats supported, but it does support a lot of the things that you'd need to see in a typical ICS environment, like ARM, PowerPC, that sort of thing. And again, you can always write more. And there are community-developed plugins that have more support as well. It does support 6502, which is nice. Hopper is a new one. It's Mac and Linux specific. I haven't used it, but people really seem to like it. Supports the things that I would want to see in sort of a basic disassembler, especially for ICS stuff. It's not a great candidate for vintage stuff, but I mean, again, there are plugins for things like 6502 and TI DSPs and that sort of thing, and it is actually a lot cheaper. Binarium is another one that I haven't even looked at yet, but it looks like it has a very similar feature set that you might like. So that's about it for getting in, and I promise the rest of these slides will go quickly. There will be a little bit of a question time before we're actually, it's time to get out. So we're going to talk about how we protect them. So, well, this slide is out of order. This was supposed to be in the red team side. So how do I protect or protect against these systems? Number one, of course, replace them or upgrade where it's possible. We've already gone over the reasons why that doesn't happen. There are lots of good reasons, lots of bad reasons for that. But when you can, and where it's feasible, replace them. If you can't, isolate them as much as possible. You know, these systems, you should treat them as fundamentally unpatchable, so the trick is to put as many things in the way of them being exploited as you possibly can. So sandboxing is an obvious one. There is no reason you should be running, you know, a vintage Mac or something on Windows 3.1 on the same network as your production servers. Don't do it. And you know, you may have to do things to route those protocols over whatever your gateway is, but it will be worth it from a safety standpoint. You know, DECnet doesn't route over modern IPs, but Cisco routers often have ways still of routing that. So place gateways, firewalls, what have you, in the way of these things so that people can't just get full access to them. Also, audit them. You need to have a good inventory, as with everything in security. Know what your computers are, know where they connect. You don't want someone saying, oh yeah, that Ethernet cable that just threads directly through the drywall there. No one really knows where that goes. Know where it all goes. And listen. Make sure that you have some sort of monitoring solution that is actually monitoring for non-IP networking protocols. You should be doing this anyway, because in an IP-only network, if someone starts doing that, it's a sign that they're probably up to no good. But definitely, if you have any of these machines, you need to be listening for them and logging and knowing what to look for. And yeah, what if it just won't die? If it's mission critical and irreplaceable, try to find a way to replace it. Again, you can accomplish a lot with sandboxing. You might have to do custom code to route stuff and firewall it and all that. You may even need unusual hardware. Like Cisco routers, again, can still route some of those old protocols. You may need to get an older router and older interface cards for them, but it can work. You should hire the cranky old people who have big opinions and pay them well enough that they will stay. Because they will actually know the pitfalls that you should be looking for on these networks better than someone just out of college who wasn't born when the computer was built. Which doesn't mean they can't know it. It's a likelihood thing. And again, make sure you have visibility. You may have to write your own logging and monitoring code using BPF and other things to find custom or unusual protocols. And make sure that your SIEM knows what to look for, what to flag, and that your SOC also knows what to be looking for coming from the SIEM. You don't want lots of false alarms, but you also don't want total ignorance. So the last part, how and when do I replace them? So how to replace these things? You need to fully examine the cost and risks of replacement. So obvious, again, for big ones like ICS, if you're talking about replacing something that controls a steel mill that could kill people if it goes wrong, that's a big cost. And you need to absolutely make sure that the thing that you're replacing works correctly before you do it, which means a lot of time, a lot of documentation, and a lot of research. Some of the subtle things can be easy to miss. What if there's this really subtle race condition that causes some terrible cascading chain that ends up blowing something up? It happens. Do you really remember everything that this was connected to? Is there some modem bank running somewhere that some system maintenance thing out in Peoria needs to connect to, or it's going to stop billing your important customers? And don't forget OSI Layer 8, which is politics. There's always going to be someone attached to the existing system, and there's always going to be someone who wants to get rid of it. So figure out how to correctly leverage those things and satisfy those players, and you'll get a lot farther than just fighting. Make backup plans for if something doesn't work like you expected. These replacements aren't easy. Things break. And consider partial solutions. Emulation is very popular. A lot of nuclear power plants are still running on PDP-11 code, but not physical PDP-11 machines because they're not very maintainable. Emulation works well. I think parts of our traffic control system work on emulated HP minis as well. And a lot of them can even interface with old hardware. Be very wary of off-the-shelf silver bullets. Something that says, oh, you got an old VAX, put this box in your network and it'll replace it. Sometimes they work. A lot of times they're snake oil. So you have to be super careful about what you trust with those things. When do you replace these things? Well, if they're well maintained, they should evolve naturally because you should be replacing things when they're a couple years old and starting to get EOL rather than 20 years old and, oh my God, we have no idea how to replace it, which happens a lot. Addressing long-held technical debt is always a difficult sell to management because it costs more the longer you wait, and they're even less likely to want to do it. The if it ain't broke mentality is pervasive, but it doesn't consider whether it's going to be a catastrophe if it does break, like, a bridge. If a bridge breaks, it's bad news, and you should have fixed it beforehand. It can help to account for the long-term financial benefits of upgrading and replacing compared to the cost. So like lower power consumption, longer uptime, lower breach risk, lower risk of catastrophic failure, etc. If the system is officially EOL, you should be trying to find a good replacement. You shouldn't be trying to hang on to it unless you have an extremely good reason. That concludes my talk. We have like 3 minutes for questions, if anyone has any. But if you want to contact me, there's the info. If you want to learn more about vintage computers, there's some resources to connect to. I've seen at least one VCF member already here. So, questions? Yes? Speak loudly.
Do you play with Newton?
I know many. I have a long time ago. I know many people who do. You mean the tablet, right? Yeah. We have VCF members who actually have whole collections. Good machines.
But are there good debugging tools for them?
Almost certainly. It's not in my domain, but I'm sure you could get easy pointers on any of these lists for it, though. Other questions?
I guess just a comment about hardware emulation. You go out today and buy an Avaya enterprise phone system, they deliver you an HP 1U server that's emulating an AT&T mainframe from the 80s. And
Is that 3B1?
same code base as a 1970s long-distance telephone switch. But
Yep.
they kept on forward, so the old stuff is still there.
Yep. Never goes away. I didn't even touch IBM mainframes, which are still running code from the 60s in some cases, but IBM has made a significant investment in making sure that stuff still works right. So, yes. Any other questions? Nope. Thank you for coming to my talk. I appreciate it.